This set of notes is all about charges. Some review about electric charge, probably from just life that you've known. One is that opposite charges attract, so a positive and a negative will attract one another. Second, like charges repel. Two negative charges will repel one another. And then lastly, this is probably new for you, but the electrons are going to be the subatomic particle that moves from atom to atom or object to object. The protons are going to be staying in place in the nucleus. Well, let's look at an electron for a moment. What is the charge of an electron? Well, the charge of an electron is 1.6 times 10 to the negative 19 coulombs. So Q means charge, and it is negative because electrons are negative. Negative 1.6 times 10 to the negative 19 coulombs. C stands for coulombs. And the mass of an electron, M, is 9.11 times 10 to the negative 31st kilograms. These are things you may or may not have known about an electron, but you need to know them. So we've got the Q of an electron and the mass of an electron. Now, while we're talking about masses and charges, let's talk about a proton really quick too. We know that, in past classes, we've kind of talked about the electron having a charge of -1. We're just counting, basically, how many electrons that there are. But it's, when you talk about actual charge, it has a unit of coulombs, and it's not a count of electrons. The charge of a proton, as you can imagine then, since usually you hear of the charge of a proton as being +1 and an electron being -1, but they have the same charge, just opposite signs. So the charge of a proton is going to be positive 1.6 times 10 to the negative 19 coulombs. You do know, though, that mass of a proton is much greater than that of an electron. You probably learned that in chemistry class. The mass of a proton is 1.67 times 10 to the negative 27 kilograms. So these four things are things you're going to need to have at your fingertips as you're solving problems. Let's talk about how we got them, though. But we do also have to talk about what a coulomb is. And a coulomb is an amount of charge, and the definition of a coulomb, so imagine I had 1 coulomb of charge. That would mean that I had, in that 1 coulomb of charge, a lot of electrons. Specifically, I need 6.25 times 10 to the 18th electrons. So 1 coulomb is equivalent to 6.25 times 10 to the 18th electrons if we're looking at negative, and protons if we're looking at positive. For a long time, we had a charge to mass ratio of an electron known, but we didn't know either the charge or the mass. We just knew the ratio of the two. And so Robert Millikan did an experiment where he had tiny droplets of charged oil moving through what's called an electric field. And the electric field exerted a force on the charged droplets, and based on how they fell, he could figure out exactly how much charge each droplet had. And what he found was every single droplet had a charge that was a whole number multiple of this quantity, 1.6 times 10 to the negative 19th. So what he figured out is that the charge of an electron is quantized, which means it has to be exactly this amount. You can't get an electron that has a charge of 1.6 times 10 to the negative 19th. It's going to have that exact amount, and if you have a different charge, then you have more electrons. How many electrons are missing or added to an object that has a positive 3.2, this funny looking U that stands for micro, and micro is 10 to the negative 6th. So how many electrons are missing or added to? Well, if it's a positive charge, then that means electrons have been lost. So let's write down 3.2 times 10 to the 6th microcoulombs, 3.2 times 10 to the negative 6, or 3.2 microcoulombs, which is 3.2 times 10 to the negative 6 coulombs. And then we figured out that one electron has a charge of 1.6 times 10 to the negative 19 coulombs, and so that I can get a count. And so my count would be 2 times 10 to the 13th electrons. Notice I didn't really pay attention to the plus or minus sign yet, because I'm going to do that now. The fact that the overall object is positively charged, that means 2 times 10 to the 13th electrons were missing or were lost. Now that we know a little bit about electric charge, let's look at how different materials interact with electric charge. Conductors and insulators. Electric conductor is one in which the atoms allow electrons to move easily from atom to atom. Good conductors are typically metal. Insulators are going to be things that don't easily allow their electrons to move from atom to atom. They can still receive electrons and give electrons away, so they can still become charged, but they don't let them move where they would prefer to move, preferably farther away from one another. So in the picture below, I've got a charged object and a neutral object. And then you can see that I have a piece of metal connecting the charged and the neutral object, and you can see that the charge has spread. So what actually happened is the charged one doesn't only have 6 protons, it really has a whole bunch of proton-electron pairs, but it's short 6 electrons. So what we're doing is we're showing only the protons that, in a sense, don't have an electron partner. And this neutral object also has protons and electrons, but we're not showing the pairs. We're only going to show the ones that are in excess. And so what happens is when you have something that is a conductor that connects, we're going to have the charge move from one object to another so that it can spread out. Now, if you looked at the picture, it looks like 3 positive charges went to the right, but we know that protons aren't doing the moving. So what's actually happening is 3 of the negative charges went over to the charged. And so now we've got negative, 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 pair, pair, pair. I'm left with 3 protons in excess over here, and I'm left with 3 protons in excess over here. But if you look at the wood, which is an insulator, when we connect the 2 objects, you see that charge does not move from one object to the other. Let's look at behavior of charges and objects that are charged. First thing we have to have in mind is the law of conservation of charge. Just like the law of conservation of mass and the law of conservation of energy and momentum, charge cannot be created or destroyed. So charge already exists. It just is simply moved and redistributed from one place to another. So right now we have a neutral sphere on the left and a neutral sphere on the right. If we connect the 2 with a conductor, we could certainly move things over, move electrons from one to the other, and then get one positive and one negative. Now there are going to be 3 ways in which we transfer charge. 2 of the ways require contact. So the 2 objects must be in contact with one another during the transfer of charge. There's another way that charge is moved, and it's through it's not contact, and that's referred to as induction, which I'll get to more in a minute. You're probably very familiar with charge from friction when you rub your feet, as you drag your feet across the carpet, particularly in the winter. You leave behind electrons on the carpet, most likely, and you become positively charged. And you notice this because when you go to reach for something metal, you get a shock. And that shock is often a result of big charge differences between 2 objects. So friction is when you have 2 objects rubbing together. And this picture has a balloon and a girl's head. And one of the objects has a greater electron affinity. It just means that one of the objects wants electrons more than the other. And so electrons are rubbed off from one object to another. With friction, you're always going to end up with one object being positive and one object being negative. As far as which object has a greater electron affinity, we're not going to expect you to know how to do that, but the two common examples that we'll use in labs and activities are rubber rods and wool or fur. And so if I have a rubber rod and I rub it with wool or fur, the rubber rod ends up being negative, and you'll see that in an activity later. And the other one that we will use is a glass rod and silk. When you rub a glass rod with silk, it turns out the silk has a greater electron affinity. And so the silk will become negative and the glass rod will become positive. The second way of charging is through contact, and I've already illustrated this a couple slides ago. When you have two good conductors and they touch one another, then charge moves easily from one to the other and can spread out when it does move to the other object. So you can see this picture here. There's on the upper right hand corner, we have the Q. This is going to be a certain amount of charge, and then I have an identical object here that is uncharged. And as they come together, because they are identical in size and surface area and shape, then it's going to spread the charge out equally, and so they're each going to take on half. There's a special type of conduction known as grounding. Grounding is when you have an object that's in contact with the earth in some way. The earth is like a bank. It's a bank for money, an earth for charges. And so there's an unlimited number of positives and negatives that we can take from the earth. If you have an object that is very, very, let's call this an insulating stand, so that they're not in contact directly. But suppose I have an object that is very, very negative. It doesn't like to be negative. And then I somehow connect that object directly to the earth. It's called grounding. What happens is then the electrons move off of the object and are deposited into the earth. And throwing a few extra electrons into the earth doesn't do much for the earth's overall charge, but it makes a big difference for the object. And same if the object was positive. We could pull electrons from the earth to make the object neutral. Now, one thing to think about is that grounding doesn't always just make something neutral, which I'll show you in a few slides. The third way of charging is through induction. And induction is when two objects are near each other but do not actually touch. During the process of the objects coming nearer to one another, they can attract or repel. And so let me give you an example. Suppose I have a positively charged object placed near a neutral object. Oh, this is actually going to be like a balloon, and this is going to be like a wall. What ends up happening is as this positively charged object gets brought nearer and nearer to the wall, the electrons in the wall, since they're free to move, are going to be moved in the way that they would be attracted or repelled. And since this is positive, electrons are attracted. So what would happen is the electrons would move so that they are closer to the positively charged object. And so I'd get what we would say as a regionally charged object. What that means is the wall itself is not charged. It hasn't lost or gained electrons. But the front of the wall is going to be negatively charged because there's more negative in the front of the wall. And the back of the wall is going to be more positively charged because the electrons have left the back of the wall. And that's what induction is. If you have a moment, I would highly recommend that you click on this PhET link. It does a nice job of allowing you to see how things move when you have charges. I mentioned I was going to show you what happens with grounding and induction, and I want to do that really quickly before we move on. Suppose I have a neutral metal sphere that's on an insulating stand. And then suppose that I bring near it an object which is charged negatively. And I bring it to the left side of the sphere. What's going to happen is the negatives in the sphere are going to be pushed to the back of the sphere. So I'm going to take the electrons and I'm going to move them to the back of the sphere because they're being repelled. Okay, now suppose that I were to ground the sphere. Suppose that we have, the earth and somehow I connect it maybe through a person, through touch, but I connect the right side of the sphere to the Earth. Well, the electrons now can move all of these electrons can actually move farther from that charge, and so they end up leaving the sphere completely. And if the electrons have left the sphere completely, now what charge is the sphere? It has an overall positive charge. So this is an example in which grounding actually ended up charging the object that was neutral. So now that we've spent some time looking at how charges push and pull on each other, let's look at how much force that they exert when they do push and pull on one another. What factors might determine how much force is between charges or charged objects? And as you probably already figured out, one is how close they are to one another, so distance. The closer the charges are to one another, the more force they're going to exert on one another, and the farther they are, the less force they're going to exert on one another. The second factor that determines how much force is between two charged objects is going to be the charge on object 1, and the third factor is going to be the charge on object 2. If the objects have more charge, then there's going to be more force between them. If one of the charges has a bigger amount of charge than the other, does it pull more greatly on the other? And the answer is no. Newton's third law, for every action there's an equal and opposite reaction. It does not matter if the charges are the same or different, they're going to pull each other with exactly the same amount of force. And that amount of force is determined by Coulomb's law. Coulomb's law says that force is equal to K, which is a constant, Coulomb's law constant, times Q1, remember Q stands for charge, so the charge of object 1 times the charge of object 2, divided by R squared, and R is the distance between the charges. The units, force is going to be in newtons, charges are going to be in coulombs, distance is going to be in meters. Coulomb's law constant is 9 times 10 to the 9th newtons times meters squared over coulombs squared. As you look at this equation, it may look a little familiar. This is going to be the force between charges, also known as the electric force. But we've had an equation that looked very similar before when we did gravitational force. The gravitational force was some constant, and that constant, capital G, was 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared, times the product of masses, and so very similar. There's the constant K for the force between electric charges, and then you see that in the gravitational equation, there's the product of the masses, m1 times m2, where in the electric force equation, there's the product of the charges, q1, q2, and then it's divided by the distance between the objects squared, r squared. There are a lot of parallels between electric force and gravitational force. The biggest difference between them is, however, one, the constants, the sizes are very different. Electric force is in the order of 10 to the 9th power, where the gravitational force is 10 to the negative 11th power, so very different in the magnitude there. Also, electric forces can be attractive or repulsive, where gravitational forces are only attractive. I should also mention that since we're going to have charges of opposite signs, positives and negatives, when you use the electric force equation, kq1, q2 over r squared, you're going to use the absolute values of q1 and q2. Don't plug in negatives. We'll figure out the direction of the force later, kind of like when we do weight equals mg. We don't plug in negative 9.8. We say mass times 9.8, and then we draw the vector going down, and then we use that idea to figure out overall net force. It's the same idea. With electric force, we're going to find the magnitude always of the electric force, and then we'll determine direction. Notation that I might use occasionally to help keep things straight when there's lots of forces is, for example, F12. F12 stands for the force on object 1 or charged 1 because of charge 2. And so if I look at A, we've got a positive charge number 1 and a positive charge number 2. They're going to repel one another. And so object 1 is going to feel a force to the left because of object 2. Object 2 is going to feel a force to the right because of object 1. And so we can figure out the magnitude, but we also have to think about direction. So I talked about Coulomb's law constant and what it stands for, but as far as what does it truly mean, it's easiest to think about it in terms of a whole coulomb of charge. So what I have pictured below is a coulomb of charge held a meter away from another coulomb of charge. So what is a coulomb of charge? Remember, a coulomb of charge is a lot of electrons, 6.25 times 10 to the 18th electrons. So if I have a whole lot of electrons, 6.25 times 10 to the 18th, and we hold that away 1 meter away from another 6.25 times 10 to the 18th electrons, then those two coulombs, they'll push on each other with a force of 9 times 10 to the 9th newtons. The rest of the slides are sample problems, so feel free to try them and then go back and play the video and see how you did. What is the magnitude of the repulsive force between two protons separated by a meter? And what is the magnitude of the attractive force between these two protons that are separated by a meter? Well, they are repelled because of their charge, but they are attracted because of their mass. So the repulsive force will be the electric force, and the attractive force will be the gravitational force. So I've written down that the electric force is equal to Q2 over R squared, and K being 9 times 10 to the 9th newtons meters squared over Coulomb squared. Remember, the charge of a proton is the same as an electron, 1.6 times 10 to the negative 19 coulombs. And the other proton with the same charge, divided by 1 meter squared. And I get that the amount of electric force is 2.3 times 10 to the negative 28 newtons. And now the magnitude of the gravitational force is going to be given to us by the gravitational force equation. So the gravitational force, G, m1, m2 over r squared. G is 6.67 times 10 to the negative 11th newtons meters squared over Coulomb squared. The mass of a proton, 1.67 times 10 to the negative 27 kilograms. And I ran out of space, so instead of writing it a second time, I just squared it, and then divided by 1 meter squared. And I end up getting that the attractive force has a magnitude of 1.9 times 10 to the negative 64th newtons. So the protons are attracted because of their mass far less than they are repelled because of their charge. Next problem, at the point of fission, a uranium atom is divided into two spheres, each with 46 protons, and a radius of 5.9 times 10 to the negative 15 meters. What is the repulsive force between them? So at the instant that they divide, assuming that they're shown, as the picture is shown below, then you have these two atoms of 46 protons in the nucleus, which is in the center, each atom having a radius as given. It does say to ignore the electrons, just worry about the repulsive force between the nucleus. So I have 46 protons gathered at the center of the atom on the left, and 46 protons gathered at the center of the atom on the right. So how far apart are those nuclei? Well, the distance, r, which is going to be from here essentially to here, that's what r is going to be. R is really going to be twice the radius of each atom, because this is going to be the radius and that's going to be a radius. And so the distance between those two groups of charges is going to be twice the radius of each atom. So now we're ready to plug in the electric force, being K times Q1 times Q2 over R squared. So K, 9 times 10 to the 9th times Q1, and Q1 is going to be the charge of object 1. And so it's 46 protons. Each proton has a charge of 1.6 times 10 to the negative 19 coulombs. So here I have that the K, 9 times 10 to the 9th, newtons meters squared over Coulomb squared, and I said Q1 was the charge of the one on the left. There was 46 protons, each proton having a charge of 1.6 times 10 to the negative 19 coulombs. So that's Q1. Since Q2 is exactly the same, I'm just going to put a squared here instead of writing it out a second time. And then I do have to divide it by the distance between those two squared. And we said that the distance between them was going to be twice the radius. So again, I have 2 times that radius, but remember I always have to square it. And so I end up finding that the amount of force between those two atoms because of the nuclei is 3.5 times 10 to the third newtons. A lot of force that causes those atoms to separate very quickly, which is fission. All right, the next 2 examples have more than 2 charges involved. The first one, Q1, which is going to be a positive charge, Q2, which is going to be a positive charge, and Q3, which is going to be a positive charge. It says find the net force on Q2. So here's what I'm going to do first. I'm going to think about the forces acting on Q2. Okay, so first of all, I can say that since Q1 and Q2 are both positive, they are pushing each other away. So the direction of the force on charge 2 due to charge 1 is to the right. And then if I were to repeat that same process looking at charge 2 and charge 3, they're both positively charged, so they're going to be repelling each other. So on charge 2, the force on charge 2 because of charge 3 is going to be to the left. So if I want to figure out what the net force is, I'm going to have to look at both F21, the charge on 2 due to 1, and F23, the charge on 2 due to 3. And since they're in the opposite direction, I'm going to have to subtract them. Whichever one is bigger, then that will be the direction of the net force. So let's start with F21, K, Q1, Q2 over R squared. So I've plugged in K, 9 times 10 to the 9th. Q1 is 2.2 times 10 to the negative 9th coulombs. You may also see this at some point. Negative 9th is the same as nano, so nanocoulombs. And then Q2 was 3.5 times 10 to the negative 9th coulombs, and then divide by the distance between the two of them, 1.5 meters squared, which gives me 3.08 times 10 to the negative 8 newtons. And as a reminder, force on object 2 due to object 1 was to the right. And so I'll repeat these steps with F23. F23 is going to be K times Q2 times Q3 over R squared. So the amount of force that charge 2 is feeling due to charge 3, 4.25 times 10 to the negative 8 newtons, and that's going to be to the left. And so finally, we have that the net force is going to be the bigger force, which in this case is F23, minus the smaller force, which is going to be F21. So 4.25 times 10 to the negative 8th minus 3.08 times 10 to the negative 8th gives me 1.17 times 10 to the negative 8 newtons. And since the bigger one is pointing to the left, then the net force is also going to be to the left. In this last example, I am using the same charges and they are spaced apart from Q2, the same as they were before in terms of distance, but I've arranged them slightly different so that we can see the answers. If you remember, since Q1 and Q2 were 1.5 meters apart in the previous example, Then the force that was on charge 2 due to charge 1 was 3.08 times 10 to the negative 8 newtons. And they're both arranged in the same way as they were before. So Q1 feels a force to the left, and Q2 feels a force to the right. So F21 is going to be to the right. And then the other one was F23, and F23 was 4.25, because it's the same charges and they're the same distance away, times 10 to the negative 8 newtons. These two are also repelling each other. So the forces are going to be up and down. So they're repelling each other, they're both positive. Q2 is going to be pushed up, Q3 is going to be pushed down. So the force on 2 due to 3 is up. In the last problem, we were able to subtract the two forces to find the net force, but when one is to the right and one is up, I don't subtract. I'm going to draw out a triangle. I've got F21, which is to the right, and then I have F23, which is up. The net force is going to be like this. And this is going to be my net force. And remember, to find the net force, we'll have to do Pythagorean theorem. So I'll take the square root of F21 squared plus F23 squared. So 3.08 times 10 to the negative 8th squared plus 4.25 times 10 to the negative 8th squared. And I end up getting 5.25 times 10 to the negative 8. And that's the magnitude of the force, but I do need to describe the direction. So what I need this theta. And so one of the things I can do is tan theta is going to be F23 over F21. And so then I can get theta to be 54 degrees. And so 54 degrees above the positive x-axis. And that would be the direction.